100 million miles from the Earth lies a gigantic spherical mass of 2 billion tons of hydrogen and helium. Within the center of that object, self-gravity exerts an internal pressure exceeding 25 petapascals, and temperatures reach an unimaginable 15 million degrees Kelvin. So extreme are these conditions that it causes some 600 million tons worth of protons to fuse together into helium in each and every second of its now 5 billion year history. 8 minutes later, less than a billionth of those photons intercept our planet. This nourishing light powers our planet's biosphere and warms our rocky abode against the empty cold of space.
The sun is our great provider. Without it, nothing could survive. But for an object as massive, as powerful as a star, it can just as easily take away life as it can provide it. Be it a violent coronal mass ejection or variable episodes of changing luminosity, we are ultimately at the whim of our home star. Unfortunately, the sun seems to be just about the only constant in our lives. Its output is very stable. It rarely threatens the Earth. It has been almost paternally looking after its daughter, the Earth, since our inception.
But is this typical? What about other stars? The idea that the Earth could be unique or rare is certainly familiar, but when it comes to our sun, we've long assumed that it's pretty typical, just another grain of sand along the cosmic shore. But now we're starting to see clues that something might be different, that our home star might be special. So join us today as we explore the rare sun hypothesis. In 1543, the German astronomer Nicolaus Copernicus published his magnum opus, De Revolutionibus Orbium Coelestium, just before his death. His radical idea was that the Earth was not at the center of the cosmos, but that it was just one of many planets orbiting the Sun. It was the first of the great demotions that astronomy would inflict upon our presumed divine status as residing at the center of the universe. In 1838, Friedrich Bessel was able to use parallax to measure the distance of a star, 61 Cygni, showing that it had to be roughly 10 light-years away, and thus meaning that the object had to be incredibly intrinsically luminous, just like our Sun. Astronomers soon realized that the Sun was just another grain within a field of millet, a galaxy of stars in which we reside. Another demotion. In 1917, the American astronomer Herbert Curtis determined that novae within what was then called the Andromeda Nebula were in fact 500,000 light-years away, more distant than any of the local stars by far. This began the Island Universes hypothesis, which proposed that Andromeda and the other spiral-shaped nebulae were in fact other galaxies. Once again, our place in the universe was demoted. With the work of Edwin Hubble observing distant galaxies in the years that followed, cosmology matured, and we realized that the very idea of a center was flawed. We live on a vast surface beneath which we cannot see.
These Copernican demotions embody what is now often referred to as the principle of mediocrity. And it teaches us that every time that we have thought in history that we were special, be it the Earth, the Sun, or even our galaxy, we were wrong. We were humbled by our study of the cosmos.
And so although we have no evidence for life elsewhere in the universe, many have reasoned that we would be making the same mistake as our ancestors, one often guided by divine arrogance, to assume that life is special to the Earth.
Perhaps, but if life isn't a distinct chemical phenomena, and more like a member of a continuum of possible chemical pathways, then we may be just a snowflake, one of trillions of ways in which chemicals can be arranged and behave, but nothing intrinsically special about this arrangement, this snowflake, except whatever specialness we elect to assign to it. And that would be the ultimate humbling, the ultimate mediocrity.
The prevalence of life may still be unclear to us, but when it comes to astronomical objects like planets and stars, surely here we can have some confidence that the Copernican principle of mediocrity is correct. After all, isn't this what the revolution was about in the first place?
This view was perhaps most famously challenged by the so-called rare earth hypothesis, the idea that conditions here on Earth might in fact be incredibly unusual. Popularized in the classic book Rare Earth by Peter Ward and Donald Brownlee, the idea is really simply that conditions here on Earth might be both incredibly unusual, but also essential for the emergence of life and intelligence.
We'll leave a detailed discussion of this concept for another day, but the idea of a rare Earth is attractive because it resolves an apparent paradox posed by the Copernican Principle. Mediocrity tells us that stars, planets, and even habitable zone rocky worlds should be common. So why don't we see any evidence for extraterrestrial civilizations out there in the cosmos? The rare Earth hypothesis flies in the face of mediocrity. Its jarring proposition is that our world is special, after all.
Sadly, the rare Earth hypothesis is not an idea that we can test, at least not right now, until we have the ability to probe the atmospheres of small rocky planets, measure their chemical constituency, their surface environment, orbital environment, and even internal geology. The rare Earth hypothesis remains more speculation than a testable scientific theory. Small rocky planets just don't emit much light, and testing their uniqueness will be a multi-generational effort for humanity.
But what about other stars when we compare them to our Sun? Surely the Copernican Principle is safe here. Surely when we look up at the stars and gaze at those glistening lights, we can be safe in the knowledge that they are just like our own Sun. Well, certainly in that last example, the answer is no. 90% of the stars in the cosmos are so-called main sequence stars, which means that just like the Sun, they are neither in the throes of birth nor death. But when we look up at the night sky, only 40% of the stars that we see are main sequence. Giant stars are rare, but they're so bright that they get overrepresented.
In a way, stars are a bit like people. In any given room, most people talk at a normal level, but there's always those louder individuals, and because of their loudness, they get noticed more. And giant stars are just that. They're just so much brighter than most dwarf stars that they're more apparent. In astronomy, we call this Malmquist bias. You can remember that next time you're at a cocktail party with a loudmouth.
Okay, fine, but that's just the stars that we can see. If we took an unbiased survey, surely the Copernican Principle holds. Surely then sun-like stars would be common. Well, again, not really. And it somewhat depends on what you mean by sun-like.
If by sun-like we just mean stars which are main sequence, then sure, the Sun is pretty common. But if we use a bit more precision, and we ask how common are stars of the same stellar classification as our Sun, then the answer is quite rare.
Just 2.7% of main sequence stars are G-type yellow dwarfs. That's calculated using the Mamajack Spectral Classification Index and the Krupa initial mass function. Smaller K-type orange dwarfs make up 9.4% of the population. And M-type red dwarfs make up a whopping 3/4 of the sample. In fact, if you were to pick a random main sequence star, you're nearly 30 times more likely to pick an M dwarf than a G dwarf.
Now, this isn't just a pointless issue of taxonomical contention. M dwarfs are completely different beasts compared to the Sun. For instance, when you look up at the night sky, none of the stars that you can see will be M dwarfs. And that's because these stars are so intrinsically faint that we just can't see them, at least not with the naked eye. A good example of that is Proxima Centauri. It is our nearest star, just 4.2 light years away, and yet, if you're in the southern hemisphere, you cannot see it with the naked eye.
Their faintness is due to their lower mass, which in turn means that their internal pressures and temperatures simply cannot support the same level of fusion output that our Sun can sustain. It's not just their output which is different, their internal structure is also quite distinct. For example, the Sun has two bulk zones, a radiative zone surrounding the core and a cooler convective zone near the surface. But M dwarfs are so cool that the convection zone consumes the entire star. Not surprisingly, these stark differences mean that M dwarfs have very different activity levels to the Sun. For example, their surfaces are often covered with far more spots than our Sun, even covering the majority of the surface in some cases. Many are seen to exhibit frequent and powerful flares from their surface, and again, Proxima Centauri is an excellent example of this. And these differences are major concerns to astrobiologists. The flaring in particular could be a real showstopper for life, with the potential to strip a planet of its atmosphere entirely, leaving them exposed to the vacuum of space. And on that basis, there has been a growing chorus of voices in astronomy arguing that our search for life should prioritize G-dwarfs over their M-class brethren, in spite of the greater observational challenges that G-dwarfs face for many planet detection methods.
Let's leave aside the M dwarfs then and just focus on stars of the same stellar type as the Sun, G-dwarf stars. Surely here we can be safe in using the Copernican logic. Surely now the mediocrity principle persists. Well, certainly at face value, the Sun appears fairly ordinary. For example, about half of all G-dwarf stars live in binary star systems, so the fact we live around a single star system isn't that unusual. Now let's look closer at the finer grained detail of our Sun.
It's now that our tale turns to Kepler. Not the man, but the telescope. NASA's Kepler mission, launched in 2009, was designed to determine how common Earth-like planets were around Sun-like stars, the holy grail of exoplanet hunting. But of course, like any mission, the budget had to be kept as tight as possible. Costs were hawked, fiscally controlled. The precision of the telescope was designed to meet its goal, but not a dime more.
Its launch date was pushed back in January 2006 in the face of budget cuts, and just a few months later, further budget constraints meant they had to replace the gimbal-led antenna, which could point in all directions, with a fixed antenna. And as a result of that, they now had to sacrifice 1 day per month to point back at the Earth and transmit data. Kepler was unquestionably a lean mission.
To determine the design and longevity of the telescope, astronomers had to evaluate the expected signal-to-noise for an Earth around another sun. A key source of noise was expected to be the stars themselves, but only the Sun had ever been measured at this level of precision before. Only Hubble would have been capable of doing this for stars other than the Sun, at least prior to Kepler. So by monitoring the Sun, astronomers had determined that it was in fact remarkably quiet over the timescale of a planetary transit, varying in brightness by just 20 parts per million.
Invoking the Copernican Principle, it made sense to the Kepler team to assume that the noise levels of other G-dwarf stars would be similar to that of our own Sun. But with the signal of an Earth passing in front of a Sun being just 4 times larger than this stellar noise level, that meant that the instrument noise components had to be remarkably low. Nevertheless, with a nearly 1 meter aperture and a 3.5-year mission, there was a sense of optimism that Kepler would be able to deliver and detect these Earths. And of course, the budget hawks were happy that it didn't cost a single dime more than it had to.
After its launch, it not only offered unprecedented abilities to spot planets, but also to monitor the behavior of stars, especially Sun-like stars, which it specifically targeted. So it would seem like Kepler would really be able to prove the banality of our Sun once and for all, confirm the Copernican logic which ultimately guided its design. But something kind of surprising happened. 2 years into the mission, Ron Gilliland of the Kepler team showed that the Sun-like stars that Kepler had been patiently monitoring exhibited an average noise level about 50% higher than the Sun. In other words, the Sun wasn't typical, it was unusually quiet.
Now that paper didn't make the headlines back in 2011, but it was a very well-known and troubling result to those in the Kepler team. Why? Well, remember that Kepler was engineered to be just about good enough to detect another Earth passing over another Sun, assuming Sun-like noise properties. But if stars were even a little bit noisier than the Sun, then there was really no margin for error. Kepler would be overwhelmed by the noise.
So when Kepler's nominal 3.5-year mission drew to an end, the team had 0 Earths detected around Sun-like stars, and they argued that this wasn't really their fault, it was the fault in their stars.
The Kepler team thought that they could overcome this by extending the mission by 4 years. After all, if stars are 1.5 times noisier than expected, then in theory, all we need to do is collect 1.5 squared, which is about 2 times more data. And so this was successful, and when Kepler was extended, the community celebrated. 4 more years of data, Earth's lookout, here we come. But remember that Kepler was never designed with extensions or extra redundancy in mind. It was a lean mission.
So perhaps it wasn't a surprise when, in less than 1 year into that extended mission, Kepler suffered a second reaction wheel failure. These are the gyros that Kepler uses to orient itself in space. It only had 1 spare, so with 2 failures, the original extended mission could not proceed. And so when people wonder why we still don't know the frequency of Earth-like planets despite flying a mission like Kepler, something we've discussed previously on this channel, we can either blame the stars or those damn reaction wheels.
So we took a little side quest there diving into the history of the Kepler mission, but now let's come back to the main topic of this video, which is, does Gilliland's 2011 study disprove the Copernican Principle, or at least perhaps put some tension on it? Is the Sun rare?
Now the Sun is 4.6 billion years old, and during that time it's been slowly spinning down due to an effect called magnetic braking. But the stars that Kepler looked at weren't all 4.6 billion years old, they were all different ages, some older and some younger. And perhaps the reason why Gilliland found higher activity levels is simply because his sample was contaminated with too many younger cousins of the Sun, stars still in their adolescence. Maybe the Sun is typical after all, at least amongst G-dwarfs, if we could only correct for this effect. Aging stars is notoriously difficult, but recently Tim Reinhold and colleagues found a way around this. Remember that since the spin of stars slows down with age, they decided to take a group of stars with similar masses and sizes to the Sun, just like Gilliland, but further constrain the sample to only those stars with similar rotation periods to the Sun, 25 days. In their new paper, published just recently in Science, they yet again find that the Sun is quieter than average, a result which has now grabbed the headlines. Using measurements of sunspot areas dating all the way back to 1878, they show that the Sun's typical activity places it in the lowest third of quiet Sun-like stars.
Other studies that focus on the flare activity of ostensibly Sun-like stars have found that many of these stars exhibit flares which are hundreds, even thousands of times more powerful than the most powerful flares we see on the Sun, such as the famous Carrington event in 1859. Analysis of the Kepler data suggests that these super flares occur roughly once every millennium. So perhaps in this case the reason why we haven't seen any super flares is simply because our records don't extend back far enough.
Nevertheless, there is an emerging picture that the Sun, at least as we see it today, appears to be unusually quiet compared to stars of similar type. And using indirect evidence, the behavior of the Sun in the last century and a half doesn't seem to be any different than that of the preceding 9,000 years. We really do seem to have a quiet home star.
And so, borrowing from the famous rare Earth hypothesis, we might posit a rare sun hypothesis. Now, the degree to which and exactly how these lower activity levels might affect the emergence of life and intelligence here on Earth remain unclear, a subject of active debate and discussion. But I think, at least in a qualitative sense, we can argue that a quieter star is advantageous for the emergence of beings such as ourselves.
But unlike the rare Earth hypothesis, this is one which we have a shot at answering in the coming years. It's far easier to study stars than exoplanets. Copernicus's grand idea in one way remains as true as ever. Stars, planets, and galaxies are indeed very common. They litter the cosmos. But amongst those countless specks of light, stars which truly resemble the Sun appear unusual. Combining the percentages covered in this video, we'd estimate that less than 0.5% of stars can be considered Sun-like, even in the local neighborhood, and ignoring possible issues with a galactic habitable zone that we'll have to discuss another day.
We have to face the stark reality that assuming that we are typical, at least when it comes to life, is ultimately an act of faith, because the data just doesn't show that yet. We cannot blindly apply the Copernican principle to any and everything that we come across, because clearly, in the case of the Sun, it is unambiguously not a typical star. Like the crest of an iceberg peeking out of the waves, living on the surface we may be unaware of just how unusual we are compared to the bulk. For the first time in a long time, we are beginning to question the Copernican doctrine. We are beginning to ponder the unthinkable. Could our home be special after all? Guys, thank you so much for watching. I want to give a huge shout out to Tom Widdowson, Laura Sanborn and Mark Sloan for generously supporting the Cool Worlds team. Now, if you have any thoughts or questions about the rare sun hypothesis, be sure to put them down below in the comment section. And of course, as always, please do like, subscribe and share this video. It really does help us out. So until the next video, stay thoughtful and stay curious.